Everyone, I'm Dipanji from BSc Chemistry Honors, third year. Molecular spectroscopy. General introduction. Spectroscopy is that branch of science which deals with the study of interaction of electromagnetic radiations with matter. Electromagnetic radiation. The term electromagnetic radiation represents the radiant energy emitted from any source in form of light, heat, etc. Some important characteristics of electromagnetic radiation are below. They have dual character, particle character as well as wave character. For example, beam of light is a stream of particles called photons moving through the space in the form of wave. These waves are associated with electric and magnetic fields oscillating perpendicular to each other and also perpendicular to the direction of propagation as shown in figure. That is why they are called electromagnetic waves. All electromagnetic radiations travel with the velocity of light. C is equal to 2.998 into 10 to the power 8 meter per second, which is equal to 3 into 10 to the power 8 meter per second. The wavelength lambda of electromagnetic radiations is related to the frequency velocity. According to equation, C is equal to mu lambda, or lambda is equal to C by mu, or mu is equal to C by lambda. As the quantity is 1 by lambda is equal to wave number, hence mu is equal to C mu lambda. It is still very common to express mu lambda in terms of known as a unit per centimeter. When it is in centimeter, C is centimeter per second. Frequency has the unit per second. As stated earlier, electromagnetic radiation are made up of photons. Each photon is a packet of energy whose energy is given by Planck equation. E is equal to h nu, h is equal to Planck's constant. 6.6262 into 10 to the power 34 joule second is the value of it. Reason of electromagnetic spectrum. When the different type of electromagnetic radiations are arranged in the order of their increasing wavelength or decreasing frequency, the complete arrangement is called electromagnetic spectrum. The reason into which electromagnetic radiation have been classified on the basis of their source and detectors required. These limits are given in table. The different radiation differ in their physical and chemical effect because they possess different energies. The energy of a photon being E is equal to h nu hc mu, where mu bar represents the wave number. Electromagnetic radiation, wavelength, frequency range, source. First, cosmic rays. Wavelength 0.0 to 0.001, frequency infinity to 3 into 10 to the power 21, source present in outer space. Gamma rays 0.0001 to 0.1, 3 into 10 to the power 22 to 3 into 10 to the power 19, radioactive substance. X-ray 0.001 to 100, 3 into 10 to the power 20 to 3 into 10 to the power 12. Bombardment of certain metals with cathode rays. Ultraviolet rays 1 to 3800, 3 into 10 to the power 12 to 7.9 into 14. Hydrogen or deuterium discharge tube or a component of sun rays. Visible light 3800 to 7600, 7.9 into 10 to the power 14 to 4 into 14. SIR or any incandescent solid. Infrared rays 7600 to 3 into 7, 4 into 10 to the power 14, 1 into 10 to the power 11. By vibration of molecules, by heating rods of special materials. Microwave 3 into 10 to the power 8, 3 into 10 to the power 11, 1 into 10 to the power 10 to 1 into 10 to the power 7 by the oscillation of electrons in wire from alternating electric current. Radio waves or TV waves 3 into 10 to the power 10, 7 to 14, 1 into 10 to the power 11 to 1 into 10 to the power 4. Basic features of spectroscopy. Introduction to molecular spectroscopy and its difference from atomic spectroscopy. In case of atoms, when energy is absorbed, electrons jump to some outer orbit and they start jumping back with the emission of energy equal to the difference between the energy of two energy levels, resulting in atomic spectrum. However, in case of molecules, when the energy is absorbed, it may result into rotation, vibration, or electronic transition, depending upon the amount of energy absorbed. Just as electronic energy is quantized, there are only discrete electronic energy levels in atom or molecule. Rotational and vibrational energy is quantized. There are only discrete rotational and vibrational energy levels in molecule. The rotational, vibrational, and electronic energy levels of a molecule are collectively called molecular energy levels. The transition of energy can take place only between these levels. The result is a molecular spectrum. when the energy absorbed by a molecule is so large that an electron can jump from one electronic energy level to another, N1 to N2, then as the energy required for the transition from one vibration energy level to another is much less, and from one rotational level to another is still less. Hence, the electronic transition is also accompanied by the transition between the vibration levels as well as rotational levels. The complete picture of the various molecular energy levels for the first two electronic level is shown. Thus, each electronic level consists of a number of vibrational sublevels represented by V is equal to 0, 1, 2, 3, and further each vibrational level consists of number of rotational sublevel represented by J is equal to 0, 1, 2, 3, etc. Mu and J are called vibrational and rotational quantum numbers. Because of large number of energy levels involved for transition, it is evident that molecular spectra are much more complex than atomic spectra. Just an atomic spectra help in the study of structure of atoms. The study of molecular spectra gives even more information about the structure and properties of molecules such as bond length, bond angle, bond strength, shape, dipole moment, etc. Absorption and emission spectroscopy. As explained above, an atom or a molecule has a number of energy levels which are quantized. The transition takes place only between these energy levels according to certain rules called selection rules. The expression for the different type of energy level of a molecule will be derived later in this chapter. However, at this moment it is sufficient to note that the transition between any two energy levels can take place in either in two ways. The transition may take place from lower energy level to higher energy level by absorbing energy. It is then called absorption spectroscopy. And the result obtained as a result of number of transition is called absorption spectrum. The transition may take place from higher energy level to lower energy level, thereby emitting the excess energy as a photon. It is then emission spectroscopy. Then the result obtained as a result of number of such transition is called emission spectrum. In fact, a number of groups of closely spaced lines are observed. Each such group of closely spaced line is called band. Thus, a number of bands are observed. We can therefore conclude that whereas the atom gave line spectra, molecule gave band spectra. In either case, the energy of photon emitted or absorbed is given by Bohr frequency formula. E2 minus E1 is equal to h nu. In term of wavelength, lambda is equal to c by mu h c by E2 minus E1. Or in terms of wavelength, mu bar is equal to 1 by lambda v by c. It may be noted that emission and absorption spectroscopy give the same information about the energy level separation. However, the practical considerations decide as to which technique should be used. Generally, absorption spectroscopy is used as absorption spectra are easier to interpret than emission spectra. Emission spectroscopy is used only when the visible or ultraviolet incident radiations are used. In this chapter, we shall therefore mainly concentrate on absorption spectroscopy. Experimental setup. The instrument used for observing absorption spectra of a substance is called absorption spectrometer, and its principle is shown in figure 3.4. It consists of four parts: source of radiation, slit to get a fine beam, monochromator, a device for getting monochromatic single frequency, a sample cell, dispersing element which is either a glass or quartz prism or a diffraction grating, detector. The nature of component to be used depend on the nature of the radiation, reason of the electromagnetic spectrum to be used, signal to noise ratio. The analysis of any sample using an electronic instrument, IR, UV or visible spectrometer, consists of following steps. The sample is allowed to interact with some kind of electromagnetic radiation. Some suitable energy is absorbed by sample depending upon the nature of sample. This is converted into an electric current detected by electronic device called input transducer. The output of this transducer is called signal. Electric current is amplified and converted into voltage by a device known as electrical signal modifier. The modified electric signals are then converted into information that can be read on a meter or decoded on a recorder. This device's do is known as output transducer. The signal produced may be considered to be made up of two parts due to sample due to the component present along with sample or the instrument used in the measurement. The signal produced due to the part 2 is called noise. In other words, noise represents unwanted meaningless signal. Alternatively, noise may be defined as random electronic signals that are usually visible or fluctuations of the baseline in the signal. Thus, the main aim of the precise measurement is to have noise reduction or signal enhancement. As the amount of radiation absorbed by the sample depends upon concentration of the sample, the amount of noise present in the instrument determines the smallest concentration of the sample that can be accurately measured. As the concentration decreases to trace levels or the signal sources are weak, as in the case of C13 MR spectroscopy, the problem of distinguishing signal from noise becomes more and more difficult, resulting in a decreased accuracy and precision in measurement. The ability of an instrument to distinguish between signal and noise is usually expressed in the term of signal to noise ratio as by n, which in case of DC signal is given by as by an average signal amplitude average noise amplitude. A higher value of S by n implies greater noise reduction and hence a more precise measurement. It may be noted that the ratio S by n cannot be increased by simply amplification because increase in the magnitude of the signal is accompanied by a corresponding increasing magnitude of noise. The S by n ratio can be enhanced by following two ways: by hardware technique, such as filter, login amplifier, etc. By software technique, by using software algorithm such as ensemble, averaging, box, car, averaging, floor, transformation, etc. Software technique have gained importance because of built-in microcomputer in the modern instrument operations such as filtering, linearization, attenuation, which were earlier accomplished by hardware devices, are now achieved by the software built-in microcomputer component of the instrument. The most powerful software technique for the enhancement of S by n involves the mathematical operation known as Fourier transformation (FT). This is briefly described below. The conventional method of representing the data spectra by the detector is in the form of intensity of the radiation as a function of frequency. However, another method of representing the data spectrum through less common is in the form of intensity of radiation as a function of the data through less common in the form of intensity of radiation as a function of data through less common as in the form of intensity of the radiation as a function of time f. Thus, there can be two types of spectra, one in frequency domain, another in time domain. Ft contains all the information in the spectrum that I frequency contains and vice versa. I frequency can be transformed into Ft through the following mathematical operation called Fourier transformation. Ft minus infinity to positive infinity e raised to power 2 pi I mu t I mu dv. Conversely, Ft can be transformed back into I mu by inverse Fourier transformation. I mu minus infinity to plus infinity e minus 2 pi f I v t Ft dt. With a very small computer, it is possible to carry out Fourier transformation of a spectrum in a few seconds. Through spectra are generally presented in the form of intensity as a function of frequency. In the frequency domain, IV, yet it is found that it is useful to take the spectra in the time domain and then transform it into usual I mu. The advantage of doing so is briefly explained below. To observe the spectrum in the frequency domain, a good deal of time is required because scanning has to be done gradually over a long range of frequencies. However, to observe the spectrum in the time domain, all frequencies can be applied at once to the sample within a very short interval of time. Thus, it can be done only in a few seconds, unlike the frequency domain spectrum, which may require say 15 minutes to scan the spectrum. The spectroscopy based on Fourier transformation is known as Fourier transformation spectroscopy. For example, FT-NMR is very common nowadays. Similarly, we have FTIR, FTUV, etc. instead of conventional IR, UV, etc. Types of molecular energies in bone Oppenheimer approximation. A molecule usually possesses four different types of energy. Translation energy, which is due to translation motion of molecule. Rotational energy, which is due to the rotation of molecule about an axis. Vibrational energy, which is due to the to and fro motion of the nuclei without change in the position of center of gravity. Electronic, which is due to the absorption of energy by electron, resulting in the lower electronic energy level to higher. According to Born-Oppenheimer approximation, total energy of volume is the sum of the rotational, vibration, electronic, and translational energies. E is equal to ET EVEEER. Further, from the expression, different types of molecular energy derived later in this chapter have been used earlier. Also in the previous, it is found that the transition energy is negligible. Small Hans Born-Oppenheimer approximation is equal to ER plus EV plus E. Delta is equal to h by 2 pi tau h by tau. The quantity del E were expressed in the term of wave number. The corresponding quantity is called lifetime broadening equation. 4 reminds us of Heisenberg uncertainty principle, and hence the quantity in the above equation is also called uncertainty broadening. For equation 4, we observe that del is equal to 1 by 2. Thus, the shorter the lifetime of the states involved in the transition, greater is the broadening of spectral line. As no excited state has an infinite lifetime, therefore all states are subject to some lifetime broadening. The main reason for the finite lifetime of the excited states collision between the molecules or with the walls of container. It means time between collision called collision lifetime as tau, then the width resulting called collision line width. Del E COL is equal to h by 2 pi t col h by t col. In a gaseous sample, the collision lifetime can be increased and hence broadening minimized working at low pressure. The transition from an excited state to a lower state is a natural, spontaneous phenomenon, rate of which cannot be changed by changing the conditions. Thus, depending upon the natural limit to rate of which cannot be changed by changing the conditions, thus depending upon the natural limit to the lifetime of excited state, the broadening of rate result in natural line width of the transition. The lifetime of the excited state broadening rate result in the natural line width of the transition. However, the natural line width are so small that the collisional and upper line broadening dominate. Intensity of spectral line. The strength or intensity of spectral line depends upon population of state with a particular energy in relation to state, called population density of the state. Strength of incident radiation. Probability that a transition will take place between the energy level. The probability of a transition is decided by selection rule. If the transition is not allowed, a strong or intense spectral line will be obtained. If it is forbidden, no spectral line or a weak spectral line will be obtained. Similarly, greater is the intensity of incident radiation, greater is the rate at which the transition are induced, and hence stronger is the absorption by the sample. To explain how the population density of the states involved in the transition affects the intensity of the spectral line, Einstein suggested that the net rate of absorption in the presence of electromagnetic field is the resultant of the following three processes: stimulated absorption, stimulated emission, spontaneous emission. Stimulated absorption is the transition from a lower energy state to higher energy state by absorbing suitable frequency from the incident radiation. The process has been stimulated by the incident radiation according to the instant. The rate at which this occurs is given by R is equal to B rho, where the constant B is called instant coefficient of stimulated absorption and rho is the energy density of the radiation at the frequency of transition. Equation 6 represents the rate of adsorption for a single molecule. For n molecule present in the lower stage, the total rate of adsorption for transition rate will be R is equal to N into R, N B rho. Einstein suggested that the radiation was able to induce a molecule in the upper state to undergo a transition to the lower state and hence produce a photon of frequency. This is called stimulated emission. The rate of stimulated emission is given by R dash is equal to B dash rho. B dash is called Einstein coefficient of stimulated emission, where B dash is called Einstein coefficient of stimulated emission. Note that only one radiation of the same frequency as required for the transition can stimulate an excited state to fall to a lower state. Einstein further suggested that the excited state could return to the lower state not only by stimulated emission but also by spontaneous emission at a rate independent of the intensity of the incident radiation. Hence, the total rate of transition to a lower state is given by R dash is equal to A plus B dash rho, where the constant A is called Einstein coefficient of spontaneous emission. Thus, for n dash molecule in the upper state, the total rate of emission will be R dash is equal to N dash A plus B dash rho, where N dash is the population of upper state. Relatively low frequencies for rotational and vibrational transitions, the spontaneous emission can be ignored. R dash is equal to N dash B dash rho. R net is equal to N B rho minus N dash B dash rho is equal to N minus N dash B rho. Thus, the net absorption is proportional to the population difference of two states involved in the transition. Hence, the intensities will be proportional to the population difference between the two states. At any temperature T, the ratio of population of two states with energy E and E dash can be obtained by applying Boltzmann distribution law. N dash by N is equal to E minus H nu by KT, where H nu is equal to E dash minus E is equal to delta E. If delta E is large, the ratio N dash by N will be small. This will imply the population of upper state is small. Only significant absorption will be from the lower state. The stimulated emission from the upper state will also be negligible. Degrees of freedom of motion. Considered as small molecules of an atom, since almost the mass of atom is concentrated in its nucleus, and nucleus is very small, the radius being in order of 10 to the power 15, and whereas that of molecule in order of 10 to the power minus 10. The atom may be considered as mass point. To represent each mass point, we require 3 coordinates. To represent instantaneous population of n mass points in space, we require 3 n coordinates. The number of coordinates required to specify the position of mass points atoms in a molecule is called degree of freedom. A molecule made up of n atoms has 3 n degree of freedom. According to kinetic theory of matter, thermal energy is absorbed by a molecule. It is stored within the molecule in the form of translation energy, internal movement of atoms within the molecule, rotational and vibrational motion. The translation motion of molecule mean the motion of the center of mass of the molecule as a whole. The center of mass of molecule can be represented by 3 coordinates. Hence, there are 3 translation degree of freedom. The remaining 3 and minus 3 coordinates represent the internal degree of freedom. However, as already mentioned, the internal degree of freedom can be divided as rotational degree of freedom, vibrational degree of freedom. For a rotational motion, there are 2 degrees of freedom. For a linear molecule and 3 for a non-linear molecule. Rotation about axis, about y-axis, about x-axis, about y-axis, rotation about z-axis. Remaining degree of freedom for the linear molecule are equal to 3n minus 5, and for non-linear molecule they are equal to 3n minus 6. They describe the motion of the nuclei with respect to one another and thus represent the number of vibrational degree of freedom. Vibrational degree of freedom of a linear molecule containing an atom 3n minus 5. Vibrational degree of freedom of non-linear molecule containing an atom 3n minus 6. A few examples on the calculation of vibrational degree of freedom are given as below. Diatomic molecule is always linear. Vibrational degree of freedom is 3n minus 5. 3 multiplied 2 minus 5, 6 minus 5, 1. For linear polyatomic molecules such as CO2, n is equal to 3. Vibrational degree of freedom is equal to 3n minus 5. 3 into 3, 9 minus 5, 4. Similarly, for HCCH, n is equal to 4. Vibrational degree of freedom is equal to 3 n minus 5, 12 minus 5, 7. For the non-linear H2O, n is equal to 3, hence vibrational degree of freedom 3n minus 6, 3. Similarly, for HCHO, n is equal to 4, 3n minus 6 is equal to 3, or 12 minus 6 is equal to 6. In terms of coordinates, the vibrational degree of freedom represent the interatomic distance and angles needed to specify the geometry of the atomic framework with the molecule. In terms of molecular motion, the vibrational degree of freedom represent the number of independent vibrational modes that can occur in the molecule, the vibration energy being associated with each mode. The only one mode of vibration of diatomic molecule like Cu, 4 modes of vibration of linear triatomic CO2 molecule, and 3 nodes vibrations of non-linear triatomic H2 molecule was shown. To sum up, for a molecule made up of an atom, total degree of freedom 3, and further split up for linear 3 transitional 2 rotational vibrational 3n minus 5, for non-linear 3 transitional 3 rotational 3n minus 6. Now we shall take the study of different type of spectra one by one. Energy level of rigid rotor. On the basis of wave mechanics, it is seen that if diatomic molecule is considered to be a rigid thumb dumbbell joined along its line of center by bond equal to the length of the distance between two nuclei, then the allowed rotational energy of the molecule around the axis passing through the center of gravity and perpendicular to the line joining by the nuclei are given by ER is equal to h square by pi 8 pi square I j plus 1, where j is the rotational quantum number that have values 0, 1, 2, 3, etc. I is the moment of inertia or the axis of rotation. I is equal to m1 m2 by m1 plus m2 r naught square mu r naught square. m1 and m2 are the masses of atoms. m1 m2 by m1 plus m2 is equal to mu reduced mass. Derive the expression for rotational energy. Center of gravity over atomic molecule, the point which satisfies the following condition: m1 r1 is equal to m2 r2. Moment of inertia of a diatomic molecule. I is equal to m1 r1 square plus m2 r2 square. m2 r2 r1 m1 r1 r2 r1 r2 common m1 plus m2 r1 plus r2 is equal to r0. From equation 4, m1 r1 is equal to m2 r0 minus r1 r1 is equal to m2 r0 by m1 plus m2 r2 is equal to m1 r0 by m1 plus m2. Substituting these values in equation 5, m1 m2 square by m1 plus m2 का square r0 square plus m1 square m2 m1 plus m2 का square r0 square m1 m2 m1 plus m2 m1 plus m2 का square plus r0 square m1 m2 by m1 plus m2 r0 square mu r0 square, where mu is equal to m1 m2 plus m1 plus m2 is reduced mass. Now by definition, the angular moment of a rotating molecule is given by L is equal to I omega, while omega is the angular velocity, just as linear momentum mass into velocity. Angular momentum can be quantized. L is equal to under root j plus 1 h by 2 pi. J is equal to 0, 1, 2, 3 का rotational quantum number. E is equal to I omega square. The quantized value of rotational energy will be 1 by 2 I omega square I naught I omega square by 2I. Substituting the value of L, ER is equal to j plus 1 4 pi square h square into 1 by 2I h square 8 pi square I j plus 1. J is equal to 0, 0, 1, 2, 3, etc. In equation 1, pattern of energy level obtained will be shown in the figure. Evidently, spacing between the energy level increases as it increases rotational selection rule. According to the selection rule, the tension takes place only between those on rotational level 4, which delta J is equal to plus minus 1. The change in the rotational quantum number is unity. The transition J plus 1 correspond to the absorption and J minus 1 correspond to the emission. In the other words, a transition can take place from a particular rotational level to just the higher or just lower rotational level. All these transitions can take place with equal probability, whereas all other transitions are forbidden. Rotational spectra of the diatomic molecule. As already explained, the allowed rotational energies are given by expression ER is equal to h square by 8 pi square j plus 1. E is equal to h nu. Therefore, in terms of frequency, we can write mu is equal to 8 h by 8 pi square I j j plus 1. Further, as c is equal to mu lambda, v is equal to under root e, because wave number mu 1 by lambda. In terms of wave number, mu bar is equal to h by 8 pi square I c j j plus 1 b j j plus 1. B is equal to h by 8 pi square IC is a rotational constant. J is equal to 0, 1, 2, 3, etc. In equation 4, the wave number of different rotational level will be 0, 2b, 6b, 12b, 20b, so on. When a transition takes place from a lower energy level to rotational quantum number, a higher rotational level with the quantum number j dash, the energy given by ER is delta ER is equal to ER dash minus ER h square by 8 pi square I j j plus 1, j dash j plus 1 minus h square by 8 pi square I j j plus 1, h square by 8 pi square I j dash j plus 1 minus j j. However, according to the rotational selection rule, only those rotational transitions are allowed for which delta j is equal to plus minus 1. Hence, in the present case, j dash is equal to j plus 1. Substituting ER is equal to h square by 8 pi square I j plus 1 j plus 2 minus j j plus 1. H square by 8 pi square I 2 j plus 1. To express in term of wave number, we put ER is equal to h nu, h c by lambda, h c mu. H c mu is equal to h square by 8 pi square I into 2j plus 1. Mu is equal to 8 pi square IC, 2j plus 1, 2bj plus 1. B is equal to 8 pi square IC. Rotational constant has already mu in the given equation represent the wave number of the spectral line which will be obtained as a result of the transition between rotational level. Putting j is equal to 0, 1, 2, 3 for the transition, j dash is equal to 1, j is equal to 1, j dash is equal to 2, or in general form j to j plus 1, involving absorption of light energy 2b, 4b, 6b, 8b, etc. We find that the most important feature of pure rotational spectrum is that every successive lines have a constant difference of wave number equal to 2b. This is called frequency separation. More strictly, wave number separation. Thus, the separation between two successive lines mu bar 2bh by 4 pi square I. Another important feature of spectra is that intensity of different transitions are not equal. Intensity increases with increasing j pass through a maximum, and then decrease j further increases. Relative intensities of rotational spectroscopy. It is expected the relative intensity of spectral lines will depend on the relative population of energy. Greater is the population, greater is the number of molecules that can be promoted to the next level, hence greater is the intensity of absorption. But the population of a rotational energy level with a quantum number j, nj by n naught is equal to E minus Ej by kt. Rotational energy level are degenerate, and the degenerate ratio of rotational level quantum number is given by Gj by 2j plus 1. Intensity is directly proportional to Nj by n naught 2j plus 1 E minus Eg by kt. Nj plus by n naught is equal to 2j plus 1. J increases the first factor, 2j plus 1 increases where the exponent factor decreases slowly in the beginning, then rapidly as the value of j become higher and higher. The graph clearly shows the relative population and the intensity of transition first increases, reaches the maximum value, and then decreases. Type of molecule exhibiting rotational spectra. As already explained, the Gauss selection rule for the observation of pure rotational spectroscopy, the molecule must have a permanent dipole moment so that it can erect electromagnetic radiation, absorb and emit a photon. Pure rotational spectrum is only given by polar molecule, homonuclear diatomic molecules, and symmetrical linear molecule like CO2, C6, H6 do not give rotational spectra. Experimental detail of microwave spectroscopy. The source of radiation is a special type of electronic oscillator called klystron. It produces monochromatic radiation of frequency corresponding to the wavelength range of 0.1 to few hundred centimeter. Energies of corresponding to these wavelengths are same as required for rotational centimeters. The energies corresponding to these are same as required for transition. These procedure consisting in the passing the monochromatic energy of microwave through the gaseous sample of the substance being studied and measuring the intensity of transmitted radiation by varying the frequency of oscillator, observing the intensity of transmitted beam. The frequency at which absorption takes place can be determined. From these data, the structural parameter like the moment of inertia, internuclear distance can be calculated. Thank you.